So one of the biggest stumbling blocks for organic chemistry students seems to be NMR spectroscopy, and in particular proton NMR spectroscopy. So today what I want to do is go through a very simple example and just kind of show you how you start from the data that you're given and you work your way down all the way down to molecular structure. So the molecular formula that we're going to look at today is C4H8Br2. So if we're lucky enough to actually know the molecular formula, the first thing that we want to do is always try to calculate your degrees of unsaturation. So that is abbreviated as DU. And the generalized formula for the degrees of unsaturation is the number of carbons minus the number of protons divided by 2 minus the number of halogens, which I'm just going to abbreviate as X divided by 2. Then you add the number of nitrogens divided by 2, and then at the very end you add 1. So if we apply this formula, we see that we have 4 carbon atoms, and then we'll subtract 8 protons divided by 2, then subtract 2 bromine atoms divided by 2, and we have no nitrogen, so the last step is just add 1. And this turns out to simplify really easily to 4 minus 4 minus 1 plus 1. So these cancel, those cancel, and you end up getting a degree of unsaturation of 0. So just to remind everyone what this means real quick, the degree of unsaturation of a molecule basically tells you the number of pi bonds in the molecule or the number of rings in the molecule. So because this molecule has a degree of unsaturation of 0, this is telling us that we don't have any pi bonds, and we also don't have any rings in our structure. So it's a linear, very simple molecule. So the next thing that you want to do is look at your spectral data. So the way that I organize the spectral data is like this. So for every piece of data, give it a letter. So the first piece is letter A, and this peak shows up at around 2.0 ppm, and it integrates to 6 protons. And it also shows up as a singlet. So just to remind everyone what these are, this first piece of data is the ppm shift. This second piece of data is the proton count, so the number of protons. And this final piece of data is the splitting, so this is a singlet. And this shows up on the NMR spectra kind of like this. So that's what the S means, is that it's a singlet. Okay, so the second piece of data that we have is portion B, and this peak has a shift of around 3.9 ppm, and it integrates to about 2 protons, and it's also a singlet. So again, it shows up as a singlet. Okay, so now that we have all of the spectral data, we want to start from the beginning and see if we can figure out a way to very simply explain each piece of data. So let's start with peak A. Now peak A integrates to 6 protons, and it has a chemical shift of around 2. So what this is telling us is that we can either have 2 CH3s like this, or we can have 3 CH2s. Now, in terms of simplicity, you always want to go with an explanation which is the most simple. And in terms of having to explain both of these scenarios, having only 2 groups to explain versus 3 groups to explain is going to be simpler. So we will probably we'll want to try to explain 2 CH3s versus 3 CH2s. So we'll get rid of that for now and just assume that we have 2 CH3s. Okay, so the second piece of data is this peak B, which integrates to 2, and the simplest explanation for that is if we have a methylene group right here. Again, we could have 2 CHs, but that's not as simple to explain as if we had 1 CH2 group. So again, we're just going to start off with the simplest explanation and then work from there. So now that we've worked our way from the top to the bottom of all of our data, we want to double check with our molecular formula. So if we go back up here and look at our molecular formula, it was C4H8Br2. Now if we count out the number of carbons in the pieces of the puzzle that we've drawn out, we have 1, 2, 3 carbons. And this means that we're missing a carbon somewhere. So the only explanation for this is if we have a quaternary carbon. So if we have a carbon with 3 or 4 different groups which are not a proton. Because if it had a proton, it would show up on the NMR spectra. And it doesn't, so that means that there's another carbon out there that either has 4 sigma bonds, or it could have, alternatively, you could have this kind of situation with carbonyl. But again, if we look back at our degrees of unsaturation, we know that we have 0 degrees of unsaturation. So this is right out. Okay, so this is the last piece of the puzzle. Now, if we take a look at, again, our molecular formula up here, let's count up the number of protons. So we have 8 protons to account for. And if we look down here, we have 3, 6, 8 protons. So those are all accounted for. Now, the one thing we don't want to forget about are our bromine atoms. So we have 2 bromines, so we need to add that to the mix. So we have 2 bromines, and we'll just draw them out there. So now we have all of these pieces to the puzzle, and this takes into account all of the atoms and all of the groups for this molecule. Now all we have to do is put them together. So let's start off with peak A. Now peak A, again, is most easily represented by 2 methyl groups. Now, what this peak is telling us is because it's only a single peak at around 2.0 ppm, that is telling us that these 2 methyl groups are chemically equivalent. So the easiest explanation for why these 2 methyl groups are chemically equivalent is if they're both attached to the same carbon. So something like this. Now, one point to note is that this carbon, whatever it is going to be a quaternary carbon. So it's not going to be a carbon that has a proton on it, because if this was the case, these 2 methyl groups, the protons on the methyl groups, would show up as a doublet, because there's this extra proton here. But since they're a singlet, that means that this carbon has no protons on it, so it's going to be quaternary. And if we look up in our box of pieces to our puzzle, you'll see that we do have a quaternary carbon that we drew out from before. So we can redraw this part of the molecule like so. We'll draw a carbon in the middle, and we'll show it going to the 2 methyl groups right here. So we've taken care of this quaternary carbon. We'll show the other bonds. And we've also taken care of the 2 methyl groups right there. So those are used up, and the quaternary carbon is used up. So now the only pieces to the puzzle that we have to figure out are the methylene group and the 2 bromines. So the first thing, or the one place that we can start off at is the methylene group, and it doesn't really matter where you put it onto this quaternary carbon. It's the exact same thing by symmetry. So if we just draw out the CH2 like so, that is one possibility. And if you look up here, the CH2 is a singlet, so that means that we have to figure out a way to make sure that this carbon is a quaternary carbon. And the easiest way to do that is just to add the bromine to that quaternary carbon, like so. So we've taken care of 1 bromine here, and then we have 1 bromine left over, shown here. And so this is the last and only place we can really put it. And if you wanted to draw it out a little bit more pretty, you can kind of draw it like so. We'll have a bromine right there, and we've got 2 protons right here. We've got to draw the quaternary carbon. Whoops. Got to draw the quaternary carbon like so. So we've got 2 CH3s, and we've got our last bromine there. So this is what the molecule would look like, and indeed that's the right answer.